Hello there, Physics 30. Welcome to Chapter 15, Atomic Physics. Okay, atomic physics means we're dealing with atoms. All right. What's important is that they could not be directly observed. Right, they're too small, so they had to develop different models to help visualize what was happening. So what we're going to be doing is that we're going to basically talk about the first models of the atom, and then get to the next ones and the next ones. All right, and kind of how they developed and why they did. Okay, we're gonna do some math along the way. Kind of solve some problems, that kind of stuff. But what we're doing is we're kind of jumping back in time a little bit. So we've already kind of talked about light and EMR and its different models, and we were kind of into like the 1930s to 1960s. Was kind of where we stopped at the end of Chapter 14. It's kind of where that one ends. In Chapter 15, we're going to go back quite a ways to start, and we're going to talk about this first indivisible concept, called the billiard ball model of atoms. We're going to go back a bit, and we're going to work our way up. And so what you'll notice is that these theories kind of, some of the same characters we had, the same people, right? Einstein, Thomson, that kind of stuff, that kind of comes back. This also builds on our previous knowledges in Chapter 11 and 12, where we're dealing with electromagnetic forces and that kind of stuff. So you're going to kind of see a few things here as they go, okay? So if we look at our formula sheet, we have basically done everything. This is one equation we haven't done yet. And there's another one. We haven't really done equals mc squared. That's kind of a part of it. Really, if you look at it, we've done a majority of these equations, right? And what that means is that this information is going to build on previous knowledge and lead us to a more solid understanding, all right? So you still have to have that kind of a little bit of a concept of how to do chapters 11 and 12. We'll also with the theory from 13 and 14 and bring it all kind of together in 15, all right? We've also have done this. I don't think we've done all of these, right? We haven't done the atomic mass unit. That's in the last chapter. We've done Planck's constant, speed of light, index of refraction, electron volt, Coulomb's law, right? We've done all of those. So those are all done. We still have this to do, but that's not until chapter 16, I believe. All right. We haven't looked into these yet. These are going to be chapter 16 and 17 as well. All right, we've also done all of this, right? So these are kind of the main principles that if you understand all of these, you really understand Physics 20 and Physics 30. All right, so there's the issue of basically what's happening is we can only see so far, right? So scientists can see the results happening, but not know why. So what they knew is that there is basically something, and if I shoot an electron at it, it interacts, and then it can go different directions or bounce off or cause something else to happen, right? So there's something going on there, right? Okay, and so what we had to do is we create models. And reason why we create models is for the unseen, right? Things we can't see. All right, you would have learned some of this already. If you took chemistry, you might have also learned it a little bit in physics 10, like grade 10 science, but yeah, this is models, right? These are the things we're unseen, right? Especially physics, we need something, okay? Right? All right, another example of what we use models for is we model black holes, right? We can't see black holes, okay? So, vocab, if you want to stop right now and go do quick vocab and anticipation guide, right, you can do that now, but I'm just going to keep going with this video, all right? So, chapter 15 here. Okay, we're starting with Dalton. So Dalton is the first one, and he basically says, okay, all matter consists of small, indivisible, indestructible particles called atoms, and all atoms are the same, and each element. So this is kind of known as the billiard ball model, right? So Dalton has the billiard ball model. And so basically what he said is, well, like a helium atom looks like this. Hydrogen atom looks like this. And a helium atom, well, it's a little bit bigger, but it looks like that. And it doesn't matter if I try to take anything, I can't split them in half. They don't split. And when these two things hit, they bounce off like pool balls or billiard balls, right? And that kind of idea. And so that's what he has said. And well, carbon's a bit bigger, and so that one, and then, then it kind of gets this idea. But what they started noticing is that they started seeing things in the particle theory as it came along, is that there's actually stuff that happens inside these interactions, okay? And this was the kind of the accepted for a while, but it was quickly kind of, once people started researching it, they they moved on past it very quickly. Okay, this little thing doesn't work very good. It doesn't work on your Chromebooks, but if you do have a home computer, right, this is a really good thing where you can actually open this up, download it. It's a Java script, so you have to install Java if you don't have a computer. And what it can do is you can basically click the model, and it shows you the different models. And if you're shooting light at it or anything like that, and it goes from kind of the oldest model at the top, the billiard ball, all the way down to the Schrodinger model. And that's kind of an important thing. And so basically, this is that if I shoot protons or light at this, it'll just hit and then bounce off, hit and then bounce off, right? So that's the first model. Very simple billiard ball model. Everything's billiard ball. Okay. So after that, billiard ball model came the raisin bun or plum pudding. All right, model out of the atom that was developed by J.J. Thomson. Okay, this is the first kind of model of the atom that really looks into some science, and this is all based off of cathode ray tubes. So cathode ray tubes were, if you don't remember, just Google cathode ray tube demo quickly, and what it'll do if you pull up a video, and you'll remember right away. It's basically that box that has two ends like this. Right, and I think you guys were all there. Stephanie might not have been, but I think you pretty much were there for me demonstrating this. And so what I have here is you put in a tube, right, and then you pass an electric current through it, and then it glows. Right, it glows in the middle. Some kind of gas glows in the middle, right? And then if I hold a magnet to it, it makes the gas move, right? Or if I pass it through it, or if I have a wire that has current passing through it, it'll also make the gas move. Okay, so, and the gas is glowing. Okay, so there's three kind of important things. First of all, the gas is glowing. That's important. Magnetic and electric fields affect it, and the gas changes color depending on what element is in the tube. All right, so those are kind of the three things that J.J. Thomson realized in order to view his thing. Okay, so what do you notice when the magnet is placed near the cathode ray tube? Well, we have interaction. Okay, we notice interaction. It's either pulled or pushed. Is light affected by electric or magnetic fields? Well, it's affected by both. Right, it's affected by both, which tells me that the cathode ray tubes are generating light. Okay, cathode ray tubes, the cathode ray, they generate light. All right. Okay. So the one thing we're also going to talk about is that the cathode, they give different colors of light when placed across a high electric field. This is because an electron with high energy will turn to a lower state emitting a photon. If we do the change in energy, how could we calculate the wavelength? Well, that has to do with our formula sheet, which I just need to grab here. Right. Well, if I know the energy, of the photon, then I'm going to actually be able to calculate wavelength using this equation. Right. And so that's important there, is that we realize that chapter 14 is also going to come in here. Okay. So what we have here is, because cathode rays were deflected by electric and magnetic field, they must be made up of charged particles. They have to be charged, right, of some type. Okay. Thomson found the charge to mass ratio of the cathode rays and saw it was the same no matter what. So that was interesting, is that the original model, right? The original model is just saying, well, there's just a ball. It's just a ball. There's nothing inside, there's nothing outside, it's just a ball. And the ball has no charge or anything like that, right? Well, what Thomson shows here is that it has to have some kind of charge, right? And then on top of that, what he did is he did a whole bunch of different elements, and they all kind of had the same charge to mass ratio. So what was in helium, whatever charge was in helium, was also in hydrogen, was also in carbon, was also in neon, right? He saw that they all had kind of the same particles, but just in different amounts, right? And so what he said is that there's electrons embedded in the positive fluid. Okay, so this is his model, Thomson. So it goes Dalton, billiard ball, now Thomson, and his is the plum pudding model, or the raisin bread, right? And basically what it is that he said that the whole concept, the whole thing is positive. There's a big positive fluid, right? Fluid-like object, okay? And it's got electrons floating around in it, okay, just randomly spaced out, right? Okay, and so the way that it's generally drawn is this way, is a bunch of little positives to indicate that the whole fluid is positive, and then have some negatives built around it. So that's Thomson's model of the atom, which is significantly more, um, I guess, scientific than the original model of Dalton. So again, here you can't see this, but if I shoot a ray into this, right, what happens is basically it gets absorbed by the positive, excites an electron, and then kicks the electron out, right? That's kind of what he's seeing, all right? Okay, so we already know how to calculate the charge to mass ratio. So charge to mass ratio means charge over mass, right? So charge to mass ratio means charge over mass. Over mass, right? Which is Q over M. And so Thomson's experiment, and he said, okay, well, I'm gonna do an F. You should recognize this, right? He did Fm equals Fc, and then he did QVB equals MV squared R. This has already been found. And then he did that. And what he realized is that, okay, so as long as it's charge mass ratio, that's good. But he doesn't have his velocity, right? He knows the radius of the magnetic field, but doesn't have the velocity, because how do you find the velocity of electron? Well, that's when he decides he's going to find the speed selector, velocity selector. So he passed the electron through an magnetic and electric field, right? Until they equal each other, cause the electron to move in a straight line, right? And so this is all should be coming back to you a little bit from chapter 12. Chapter 12, I think maybe even chapter 11, I can't remember which one it's in more, right? And so he used this to get the V equals E over B, right? So basically, if I look at this equation up here, okay, and I'm going to put in, right, I have Q over M, and then I have that V equals E over B, right? Okay, and so it's the electric field over the magnetic field, right? And so what that leads to is this idea that this is actually going to be E over R B squared, right? So I divide by B, then I got to divide by B again, right? So it's B over B squared. Okay, so we're going to use that. Okay, a beam of electrons passes undeflected through a 0.5 T magnetic field combined with a 50 kilonewton electric field. The electric field, the magnetic field, velocity are, the electrons are all perpendicular to each other. What would happen to the beam of electron if their speed were greatly decreased? All right, so what we have here is we have kind of this idea where we have, okay, we have the force electric equals the force magnetic, right? So the force electric, we can say, is EQ, and the force magnetic is QVB. All right, so I can put numbers and stuff in there, but what I want you to note is that right now these equal each other, okay? And so what would happen if I was to greatly decrease their speed? Well, that means that V is going to go down. So what does that mean is going to happen? Well, it means that the electric field, right, if the V goes down, that tells me that force magnetic goes down, which means the electric force, right, the electric force would win. Okay, so if the velocity greatly decreases, okay, then the magnetic force reduces, so the electric force would win, right? So if I had originally, so we had in the first part, right, let's say we had Fe and Fm would be the same. The second part here, when I slow down, right, Fe would stay the same, but Fm will get noticeably smaller. And so originally the particle is going to go straight. Now the particle is going to curve in the direction of force electric. All right. So what you're going to have to do here for these questions, practice problems 1 to 11, is you're going to be looking at redoing a lot of these concepts and reopening up that idea of chapters 14 and 15. You're going to be using these two equations, all right, along with this kind of concept of M equals FC, and you're going to have to really kind of build your understanding from what you already know, okay? So a lot of this is going to be review, but you still need to kind of do it is the best way I can say that, okay? So that's the end of lesson 1, all right? You should be able to then do your vocab, your anticipation guide, and start lesson 2. Alrighty.